I'm Mitchell Medeiros.
And I'm Max Sombong, and this is Hockey Physics.
Today, me and Max are going to be talking to you about how acceleration and momentum ties into hockey and how hockey players play the game. So, let's take a look at our first clip. As you can see in our first clip, Max is pushing off the wall.
You might be wondering, how did I move? Let's start with the basics, and that is drawing a free body force diagram. Let's first start off by identifying our system. In this case, it would be me.
Then, identify all the forces on your system. Notice that in this case, the ice is frictionless.
Now, let's draw our x and y equations.
As you can see, on the y-axis, the forces are balanced and equal to 0 newtons. However, on the x-axis, since there's only one force acting on Max, the forces are unbalanced, giving him an acceleration. And what is acceleration? Well, it's quite simple. This just means that as Max is in motion, he'll gradually speed up over time.
Let's see another example of this, and with a different approach.
Now, what's different about this approach? Well, in this video, Max has 3 distinct separate motions, so let's take a look at those.
To help us get a better understanding of this, first we will have to draw out our position time graph, velocity time graph, and acceleration time graph. But first, we also have to find out what the meanings of the slopes are.
So let's start out by taking a look at our first graph, position time graph. Position is usually measured in meters and time is measured in seconds. So let's take a closer look at those units. The slope of that graph is going to be position over time, ending up in meters over seconds. That ends up being the same unit that velocity is measured in. So that's how we determine the slope of our position time graph is equal to velocity. Second, let's take a look at our velocity time graph. To find the slope, we're going to do velocity over time. And now let's take a look at those units. Velocity is measured in meters per second, and once again, time is in seconds. So, our unit will end up looking like meters per second per second. This is also the same unit as acceleration, and this is how this all ties into our third and final graph, the acceleration time graph. So now let's analyze this third graph. In the acceleration time graph, there are 3 unique motions. Each one of those horizontal lines on the graph represents Max's acceleration during the video.
So to sum it up, for the position time graph, the first segment would be my velocity increasing squared, then it would be increasing directly, and then it would be increasing squared in the negative direction. For the velocity time graph, my velocity will be increasing, then it will stay constant, then it will decrease. Finally, for my acceleration, I will experience acceleration for the first part, the second part I won't, and for the third part I will, but in the opposite direction.
It's never a good hockey game without a nice fight. Let's take a look at momentum and how that works. After witnessing the fight, to get a better understanding of momentum, let's start off by drawing a momentum bar graph. By drawing this momentum bar graph, it'll help us understand why Max went farther when I pushed him than I did.
First, we start off by labeling our systems, which will be me and Mitchell. And we will also have to determine if this was a collision that was elastic or inelastic. And in this case, we move in opposite directions and bounce off each other, so therefore it would be inelastic.
First, we start by drawing our coordinate axes to show direction. Next, we do a before and after picture. Since neither of us are moving in the beginning, our before picture has no boxes. However, our after picture does have boxes because I pushed Max. So let's take a look at that. First question is, why is Max's 1x4 and mine's a 2x2? Well, By adding another row to my side of the momentum bar graph, it shows that I have more mass than Max. So as a result, Max is going to have more boxes going to the left, meaning he's going to have a faster velocity. But let's take a quick look at the law of conservation of momentum. Even though Max has a 1x4 boxes going to the left and I have a 2x2, Max is going 4 in the negative and I'm going 4 in the positive, meaning it is still equal to 0, just like our before picture. So it's conserving momentum. Both of our pictures do have to equal to 0. Let's analyze our equation for momentum. P equals m times v. Momentum equals mass times velocity. Since I have a greater mass, I had a smaller speed than Max, but an equal momentum to him, as seen in the momentum bar graph where both are equal to 0. Since Max had a smaller mass, he experienced a higher speed, but our momentums were still equal. So, I ended up moving less than Max from the push, and Max moved more because our masses and our velocities were different. However, our conservation of momentum overall means they were both equal.
Please don't give us an F on this.
The end.